Hello. In this video, we're going to look at how to do a regression analysis in R. So for starters, we will read in our data. And just like the last example, here we're going to look at seeing if the number of siblings that someone says they have, if that predicts the number of Skittles that they estimate are in a regular size bag. So in the last video, we saw that we can create a scatter plot and we can jitter the observations if we're worried about overplotting. And we're about to perform a regression analysis here. And regression is all about lines. And so shockingly, we're going to be creating linear models because we're looking at lines. And so in this plot here, before we get to looking at the output itself, we might want to impose a regression line. And to do that, we're going to ask for a geom smooth, and we have to tell it the method is LM for linear model. And geom smooth is going to throw a line on top of this, and because we tell it to make it a linear model, it's going to be a straight line. And sure enough, we've got a straight line with a confidence band around that, and you can see up in the regions of the scatter plot where we have fewer observations, our confidence intervals here are very wide, which matches intuitively what we'd expect. Where we don't have a lot of data, we should be very unconfident about what the predicted value would be in those cases. But confirming what we saw in the last video, it looks like there might be, if anything, a positive relationship here, but nothing we'd be super confident about. Last time we expressed that as a correlation coefficient, but here let's see what it would look like in a linear regression where we express it as a 1 unit increase in the predicted value of one variable as a function of another. So to do that, as mentioned, we're going to use LM for linear model. So we're going to ask for a linear model, and here we're going to use formula notation where we say we want to predict estimate from siblings. So on the left-hand side of the squiggly line is the y value, the thing we're predicting, and on the right is the predictor variable. We have to tell it the name of our data. In this case, it's called data, and I'm going to save all this to an object called SKT for like Skittles, and then I can run this to save the model, and then I can ask it to summarize that object, and it'll show me the regression output. So here we have some information about our residuals. For each observation in our sample, the model's not perfect. It's off by some amount, and the median amount that it's off by is 3.8. 3.8 Skittles. This is in the units of the y variable here. And we have information about our intercept, and most interestingly in this case about our predictor here. So the slope is 1.84. And we have a t-value and a p-value associated with that. So you'll remember from earlier, what this is telling us is that for every 1 unit increase in x, the model predicts a 1.84 unit increase in y. So expressed in plain English terms here, that would mean this model is predicting that for every additional sibling that a person has, we would predict that they would estimate 1.8 more Skittles in a bag. So less than 2 Skittles, not a whole lot. So it sort of makes sense then that this isn't a statistically significant effect. It's also not a practically significant relationship. And then down here at the bottom, we have the R squared information about the total proportion of variance accounted for, and the more conservative adjusted R squared as well. And then finally, if we had a whole set of predictors here, we'd get an F test for the entire model altogether. Now, speaking of having more predictors, in some cases you might want to do a multiple regression where you have more than one predictor, and holding constant all the others, you can see what is the effect of each variable in your model. By the way, I'm saying effect. I'm being a little sloppy with my language here. In this case, our design is correlational, so we should be talking about prediction or relationships between variables. This wasn't an experiment, so I shouldn't be drawing any strong causal conclusions here. But for the regression itself, again, we're going to create a regression model, and here I've given it this name, SKT mult, for multiple regression, and we're going to use formula notation again, and we still have the same dependent variable, the estimate, But instead of predicting it just from siblings, I'm going to tell it to predict that from siblings and from the current level of anger, and you get the whole thing here, also from the current level of sadness, and I give it the name of the data file again. So you can see here we have 3 predictors in this case. And we can run that and we get all of our regression output. Down here again we have information about our residuals. Now, reassuringly, compared to last time, you can see our median residual is smaller than it was before. Cool. We add predictors to our model that should increase our predictions on average, and so it's nice to see that we are missing by less than we were originally. Now, again, we've got an intercept for someone with 0 siblings, and for anger and sadness scores of 0, whatever that happens to mean, we would expect them to estimate 34 Skittles, and then we have slopes for each of our predictors. And going over to the p-values on the right here, you can see none of them are statistically significant. And down here at the bottom, you can see the F statistic. Looking at the overall model, does this set of predictors explain a significant amount of variance? And they don't. And we have the multiple R squared and the more conservative adjusted R squared. These are pretty big amounts of variance explained. We have a pretty small sample, so we just can't say that much confidently in this particular case. However, maybe a bigger study would show a reliable effect. That's a question for another day. So there you have it. That is how you do a basic regression analysis in R.